Hi, Dr. P here. Welcome back to Chem 1A lecture videos. And in this lecture video on Chapter 1, Lecture 2, we'll take a look at a couple of major concepts here. One is phases of matter and classification of matter, and then we'll also look at physical and chemical properties. So let's look at some phases of matter. Now, there are some that we are familiar with, such as solid, liquid, and gas. And so solids have a definite volume and shape. For example, this pen is solid. And it has, a definite volume. I could measure the volume, and it's in a pen shape. Liquids have a definite volume, but they assume the shape of whatever container they're in. So they don't have a definite shape. So for example, I've got my coffee here, my nice W mug here. The mug itself is solid. It has a definite shape. The coffee in there is liquid. And so it assumes the shape of the mug. But it still has a definite volume. A gas, which is the last of our three normally encountered phases of matter, does not have a definite volume. So it assumes the volume and shape of the container. Now there are some other phases of matter that I like to talk about. They're getting a little passé now, but plasma TVs used to be everywhere. Maybe not everywhere. We used to have one. Plasmas are very hot. In fact, you no longer really, they're so hot it's kind of it's a superheated gas where electrons are stripped out of the atoms. And anyway, that's a plasma. We can also have a liquid crystal. Interestingly, these used in TVs. So you have plasma TVs, LCD TVs. What's an LED TV? Well, it's actually partly an LCD. There's a liquid crystal, but it's lit by LEDs, light-emitting diodes, so it's a little different. Although there are some other LED technologies like OLED, organic LEDs, that are a different technology. So plasmas are very hot. Liquid crystals have properties of both solid and liquid, sort of depending. There's one I like to talk about, which is the Bose-Einstein condensate. And if plasmas are very, very hot, then the Bose-Einstein condensates are very cold. Like we're talking a few degrees above absolute zero, a few Kelvin above absolute zero. So they're super duper cold. And they're kind of weird. It's basically in a Bose-Einstein condensate, you have a bunch of atoms in the same place at the same time. So yeah, that's kind of weird, but it's I don't know, kind of cool. And one of my friends from actually preschool went on to become a physicist, and he studies condensed matter physics, so ultra cold matter, so Bose-Einstein condensates and stuff like that, which is kind of cool. Okay, so one important thing to remember about matter is that Matter is neither created nor destroyed. And that's the law of conservation of matter. And it's specific that um, uh, the law of conservation of matter refers to particular types of changes, so essentially chemical changes. So matter is neither created nor destroyed by phase changes or chemical changes. We'll talk about what a chemical change is in just a little bit. So let me just set that aside. So we're never going to get out more mass than we start with. So if you do a reaction and you end up with more mass than you theoretically should, then something went wrong, and somewhere along the way you picked up some extra solvent or something like that. All right. So let's take a look at some other aspects of matter. We've talked about different phases and what they're like, but let's look at some different properties. And actually, before we look at properties, let's classify matter. So let's look at types of matter. So we'll say classifying matter or classifying substances. And we'll go ahead and make a list here. We can have pure substances and so pure substances are just that. They're pure. They have a constant composition. Let me just see if I've got my... So we'll say constant composition. An example of this would be something like air, the air in a room. Okay, that air is considered, actually no, sorry, air is not a good example. Let's do something like the caffeine that happens to be in the coffee. Well, this is decaf, but let's just say, for example, caffeine. Any bit of caffeine looks like any other bit of caffeine. And you can break down the caffeine, but you can only break it down into individual bits of caffeine. If you broke it down any more, it would no longer be a pure substance. Pure substances are composed of individual bits called atoms, and we'll get to that in just a minute. Let me think of a little bit different way maybe to approach this. So our pure substances could be elements or they could be compounds. Elements are made up of one type of atom, and compounds are made up of different types of atoms. So for example, an element might be something like gold. And we'll say pure gold. That is 24 karat gold. Here the K means carat. Let me write that out actually. Sorry. 24 karat, K-A-R-A-T, gold. If we have less than 24 karat gold, then that's not going to be a pure, not going to be um, an element because there's other stuff in there. And then a compound is made up of different types of atoms. So, for example, something like sodium chloride. Or what we call salt. It's made up of two elements, sodium and chloride. Caffeine is also a compound, and it's made up of carbon, nitrogen, oxygen, and hydrogen. So a bunch of different, what was I going to say? A bunch of different types of atoms. All right. So one thing I like to do is go through and sort of make a flow chart, and I think we'll get there in just a few minutes. Sometimes we have, instead of pure substances, we have mixtures where we don't have a constant composition. And in these mixtures, they could be separated by physical changes. So mixtures made up of two or more different substances. I should specify pure substances, and they can be separated by physical methods. For example, we can't separate caffeine into its individual atoms unless we do some chemical changes to it, make chemical changes to it. We could, however, separate mixtures like air. So we have two types of mixtures, homogeneous and heterogeneous. Really, the easiest way to describe these is homogeneous mixtures. All the bits look the same. And in heterogeneous mixtures, we have a composition that varies. An example of a homogeneous mixture is air. All the bits of air in this room look the same. We've got oxygen and nitrogen and a little bit of argon and carbon dioxide and water vapor. And yeah, heterogeneous mixture, well, a tasty example is a chocolate chip cookie. You can pretty clearly see that some bits are more cookie and some bits are more chocolate chip. Let's take a look at my coffee again. Here's my coffee. Now, where would it fall? Let's see. Well, it's not a pure substance because it's made up, and we're talking about the coffee, not the mug. The coffee is made up of a bunch of different things. There's not very much caffeine because it's decaf. It's got water present. There's other molecules, tannins, molecules that give it its flavor and aroma and color. I added some half and half, so we have some cream. So there are sugars from the cream and lipids, fats from the cream as well. So there's a whole bunch of different things. I swirl it around a bit and it looks pretty evenly mixed. So we know it's not an element because there's no caffeine on the periodic table. CF, the element CF is californium. Anyway, it's not a compound because it's actually made up of multiple pure substances, whereas a compound is a type of pure substance. And what type of mixture? Well, it looks pretty homogeneous. We often refer to as homogeneous mixtures as solutions. So let's just say here, homogeneous mixtures, often called solutions. Now, if I let it sit a while, maybe things would separate out. Maybe I could put it in a centrifuge and spin it really fast. I'm not going to change any of the chemical composition of any of the stuff in it, but maybe I could get the cream to separate or something like that. In which case it would be more on the heterogeneous side. Let's look at another example. Let's look at my wedding band. So here we have my nice wedding band, and if I look on the inside here, I see I've got my little inscription, and which you probably can't see, which is fine. And then I've got somewhere around here, there's a little indication, yes, Shane Company, and it should have the carats, and I really can't see it, but I think it's 14 carats. So 14 karat gold is not pure gold. So this would be a mixture of gold and silver and maybe some copper, and that would be a type of homogeneous mixture. We call that an alloy. A homogeneous mixture of metals is called an alloy. Now if you look really close, you can see that the center part is a slightly different color than the outer parts. And you can kind of see that maybe, let me turn this light on here, see if that helps. Does that help any? Not really. But you can see that inside the center bit there is slightly different. That's white gold, and the rest is yellow gold. White gold is gold, just with a different percentage of silver and copper relative to yellow gold. So because there are actually several strips there, there's yellow gold, white gold, yellow gold, we would call that a heterogeneous mixture. So my ring is heterogeneous because of those different strips of gold there, and then the gold itself is homogeneous mixtures because it's not pure gold, it's 14 karat gold. And you need to have 24 karat gold for it to be pure. We can summarize this. Let's summarize what's going on here. Give me a sec. Yes, Flint is saying hello. Flint, our dog, is saying hello again. So let's go ahead and summarize here. We have matter. We can classify matter into two types. We could classify matter as either being mixtures or pure substances. And mixtures are related to pure substances by physical changes. Mixtures can be broken up furthermore into heterogeneous and homogeneous. And again, these mixtures are related by physical differences. So I'll just write PHYS for physical. Now, on the other hand, we have pure substances, which could be compounds, they could be elements. Compounds and elements cannot be separated by, or cannot be changed by physical means. We need chemical means. So rearranging some elements into compounds, that's a chemical change. Breaking up a compound into its component elements is a chemical change. At this point, I want to mention that this is at the macroscopic level. And then if we go down to a microscopic level, or we'll call it the nano level, we see that our compounds are made up of molecules and elements are made up of atoms. Now, atoms also make up molecules. So again, our molecules and our atoms are related by chemical changes. We can have actually elements that are made up of molecules where all of the atoms in the molecule are the same. So this is not a hard and fast rule here, but it's a good way to think about it. On the macroscopic level, we have compounds which are made up of elements. On the microscopic level, we have molecules made up of atoms. When we get a whole bunch of molecules together and look at it as a big lump, that's a compound. A whole bunch of atoms together of the same type and look at a big lump, that's an element. Okay. Let's see here. Let's take a look then at some physical and chemical properties. So let me just say physical versus chemical change. And this will wrap things up. So a physical property is a characteristic of matter that is not associated with it changing composition. So these are things like density, color, melting point, boiling point, because melting and boiling are physical changes. They're not chemical changes. So a physical change is a change in the state or properties of the matter with change. Excuse me. Let me have some more coffee here. Change in the phase or property of the matter that we're looking at without any change in the identity of the substances. Well, I'm having spelling issues today. Sorry about that. So a physical change would be a change in phase or state or properties without a change in the identity of the substances. So, for example, melting, boiling, dissolving, those are considered physical changes. Chemical change, on the other hand, is one where we do see a change in the identity of the substances. And examples of these could include combustion. So, for example, if you light a Bunsen burner, you will have the natural gas, the methane, coming out the burner, and it will burn in the presence of oxygen, and you will get a chemical change and get carbon dioxide and water as a result. So combustion, rusting is a chemical change. Digestion, so as my stomach sits here and starts digesting the a little bit of milk protein in my coffee, that is a chemical change. Flint is big on chemical changes in the background there. Anyway, and so we will look at both of these, both physical and chemical changes. Oh, let me get this back in frame here. Sorry about that. We'll look at both physical and chemical changes in this course. And so one thing that you do want to be familiar with and practice is identifying types of physical change, types of chemical change. Also, types of mixtures, heterogeneous versus homogeneous, types of pure substances, compounds versus elements, molecules versus atoms. So the practice problems have lots of examples with these. One last thing to mention is two more definitions that I want to give because the text gives them, and that is properties of matter. And we have extensive properties and intensive properties. Extensive properties do not depend on the amount of matter present. An example of that would be temperature, density, and there are others. So for example, my coffee is the temperature it is. It's getting down to room temperature, so I'm going to have to go throw it in the microwave. But it doesn't matter how much of it I have, it's still the same temperature. I can drink half of it and the remaining half will still be the same temperature. Intensive properties, on the other hand, are the opposite. I'm sorry, I got these backwards. See, it's not always as easy as you think. Let's try this again. Intensive properties do not depend on how much stuff, and extensive properties do depend on how much stuff you have. So these guys depend on amount of matter present. And an example of this would be mass. Volume could be an example as well. A cup of coffee is more than half a cup of coffee, volume-wise, and it also has more mass. Um, a 2-pound chunk of gold is more mass than a 1-pound chunk of gold, so mass is extensive, but it's still the same density, so density is intensive. So, I do apologize for that mix-up there. Obviously, you can see that some of these concepts, they're easy to get mixed up. So just work on that and understand the difference between these two. Intensive does not depend on the amount of matter present. Extensive does depend on the amount of matter present. All right, well, I think I've gone on long enough. This lecture video was quite a bit longer than I had intended. So I'll try to make the next few a little bit shorter. But in the meantime, stay safe out there. Bye now.